children, I am Shubhajit and today with me is Hemalata. Welcome back to another video. Previously, you have learned about the Oersted experiment and magnetic field lines. Today, let us gather some information on the direction of the magnetic field. Learning outcomes. At the end of this session, you will be able to understand about magnetic field due to a current through a straight conductor. Right hand thumb rule. Magnetic field due to a current through a circular loop. Magnetic field due to a current in a solenoid. Keywords: magnetic field, right hand thumb rule, straight wire, circular coil, solenoid. A coil of many circular turns of insulated copper wire wound on a cylindrical insulating body. Before starting the session, let's look at this concept map. Magnetic field due to a current carrying conductor. We have already studied that an electric current through a metallic conductor produces a magnetic field around it. In order to find the direction of the field produced, let us consider an activity. Take a long straight copper wire, 2 or 3 cells of 1.5 volt each and a plug key. Connect all of them in series. Place the straight wire parallel to and over a compass needle. Plug the key into the circuit. Observe the direction of deflection of the north pole of the needle. If the current flows from north to south, the north pole of the compass needle would move towards the east. Replace the connections in the circuit, switching positive and negative ends. This would result in the change of the direction of current through the copper wire, that is, from south to north. Observe the change in the direction of deflection of the needle. You will see that now the needle moves in the opposite direction, that is, towards the west. It means that the direction of the magnetic field produced by the electric current is also reversed. What determines the pattern of the magnetic field generated by a current through a conductor? Does the pattern depend on the shape of the conductor? We shall investigate this with an activity. We shall first consider the pattern of the magnetic field around a straight conductor carrying current. For this, take a battery 12 volt, a variable resistance, an ammeter 0 to 5 ampere, a plug key, connecting wires and a long straight thick copper wire. Insert the thick wire through the center normal to the plane of a rectangular cardboard which is fixed and does not slide up or down. Connect the copper wire vertically between points X and Y in series with the battery, a plug and a key. Sprinkle some iron fillings uniformly on the cardboard. Keep the variable of the rheostat at a fixed position and note the current through the ammeter. Close the key so that a current flows through the wire. Gently tap the cardboard a few times. Observe the pattern of the iron fillings. You would find that the iron fillings align themselves, showing a pattern of concentric circles around the copper wire. These concentric circles represent the magnetic field lines. The direction of the magnetic field can be found by placing a compass at a point P over a circle. Observe the direction of the needle. The direction of the north pole of the compass needle would give the direction of the field lines produced by the electric current to the straight wire at point P. Show the direction with an arrow. The direction of magnetic field lines gets reversed if the direction of current through the straight copper wire is reversed. We can find this by the deflection in the needle in the opposite direction. If the current is increased, the deflection also increases. It indicates that the magnitude of the magnetic field produced at a given point increases as the current through the wire increases. The magnetic field produced by a given current in the conductor decreases as the distance from it increases. A convenient way of finding the direction of the magnetic field associated with a current carrying conductor is by using a right hand thumb rule. Imagine that you are holding a current carrying straight conductor in your right hand such that the thumb points the direction of the current. Then your fingers will wrap around the conductor in the direction of the field lines of the magnetic field. This is known as the right hand thumb rule. We have so far observed the pattern of the magnetic field lines produced around a current carrying straight wire. Suppose this straight wire is bent in the form of a circular loop and a current is passed through it. We know that the magnetic field produced by a current carrying straight wire depends inversely on the distance from it. Similarly, at every point of a current carrying circular loop, the concentric circles representing the magnetic field around it would become larger and larger as we move away from the wire. By the time we reach the center of the circular loop, the arcs of these big circles would appear as straight lines. Every point on the wire carrying current would give rise to the magnetic field appearing as straight lines at the center of the loop. By applying the right-hand rule, it is easy to check that every section of the wire contributes to the magnetic field lines in the same direction within the loop. We know that the magnetic field produced by a current carrying wire at a given point depends directly on the current passing through it. Therefore, if there is a circular coil having n turns, the field produced is n times as large as that produced by a single turn. This is because the current in each circular turn has the same direction and the field due to each turn just adds up. A coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder is called a solenoid. The pattern of the magnetic field lines around a current carrying solenoid is shown in the diagram. When we compare the pattern of the field with the magnetic field around a bar magnet, we find them to be similar. In fact, one end of the solenoid behaves as a magnetic north pole, while the other behaves as the south pole. The field lines inside the solenoid are in the form of parallel straight lines. This indicates that the magnetic field is the same at all points inside the solenoid. That is, the field is uniform inside the solenoid. A strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material like soft iron when placed inside the coil. The magnet so formed is called an electromagnet. Points to remember: an electric current through a metallic conductor produces a magnetic field around it. The direction of magnetic field lines gets reversed if the direction of current through the wire is reversed. The magnitude of the magnetic field produced increases as the current through the wire increases. The magnetic field produced by a given current in the conductor decreases as the distance from it increases. Right hand thumb rule. If a current carrying conductor is imagined to be held in your right hand such that the thumb points along the direction of current, then the direction of the wrapped fingers will give the direction of magnetic field lines. A coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder is called a solenoid.